Good morning, good afternoon, everyone. This is Diane Fodell. Thank you for joining our Cognitive Systems Institute speaker series. This morning we have the well-known Ken Forbus. Ken is the Walter P. Murphy Professor of Computer Science and Professor of Education at Northwestern University. He received his degrees from MIT. His research interests include qualitative reasoning, analogical reasoning and learning, spatial reasoning, sketch understanding, natural language understanding, cognitive architecture, reasoning system design, intelligent educational software, and the use of artificial intelligence in interactive entertainment. He is a fellow of the Association for the Advancement of Artificial Intelligence, the Cognitive Science Society, and the Association for Computing Machinery. He has received the Humboldt Award and has served as chair of the Cognitive Science Society. Please help me welcome Ken Forbus, who's going to present Software Social Organisms, Implications for Measuring AI Progress. Thanks for being our presenter today, Ken, and I'll turn the call over to you.
Thank you, Diane, and I really appreciate the kind introduction. So this talk is born of frustration in the AI community. That is, you keep seeing things in the popular press about killer robots and AI as existential threats. Someone who built a chatbot declaring that they've achieved true AI because they fooled some people for a few minutes, and so therefore they passed the Turing test. So as a community, some of us have been getting together and formulating more interesting evaluations and trying to figure out, well, what does it really mean to achieve human-level AI, and how do we measure that? So there's a perspective that's come out of my group that is what I'm going to be talking about today, and it's a little bit different than your standard way of thinking about AI, as if there was just one standard way of thinking about AI, and that's what I'm going to tell you about. So here's the big picture, just to tell you where we're going, that human-level AI, in my view, is going to be achieved by learning how to create sufficiently smart software social organisms. And I'll unpack the smart software social organisms and what I mean by sufficiently smart. And the implication of this is that for evaluating AI, no single test is going to be a measure for progress. It's kind of interesting. In last January, actually a year ago, January, there was a workshop on the Turing test, and about half the people realized this, and about half the people didn't. And the people who didn't were proposing new single tests. They were all well-intentioned tests, and some of them were very interesting tests, but none of them are actually capturing the flexibility that human beings have, and no single test can do that. I think instead, an appropriate measure should be evaluating whether or not these systems can participate in our culture. So think of them as apprentices working with us, alongside us, and taking on larger roles. And the interesting thing about that perspective on these systems is that it provides multiple dimensions that you can use to measure progress. And we'll talk about some of those dimensions and why they matter. Okay, so what do I mean by all this? So if you think about today's AI systems, see if this pointer works. Yes, there we go. So today's AI systems, they're kind of here. They're like drag racers. They're very fast. Stat solvers and model checkers are superhuman in terms of their reasoning capabilities. They work brilliantly on very narrow circumstances. If you have a machine learning system and you train it up with enough data on just the right situations, it's fine. You take it outside of the situations, they're not so fine. So they're not so good off-road, we could say. The other problem is all these systems require massive teams of human experts to build and maintain them. So it's about a century of work went into IBM's Watson. A stunning achievement, but it's 25 people working over 4 years on a 2-week training and testing cycle. If you want to find out more about that, there's a beautiful description in a book called Final Jeopardy by Steve Baxter, which is written as a sports story, so it's really fun. The AlphaGo effort is similar. They tune the system, they tweak the system, they hand-coded some what they call common sense rules of Go. They set the thing up with its data, they ran the system, evaluated the results, and said, no, we have to tweak it this way. And that's not what an organism is. And by the way, in terms of speed of learning, if you look at the number of games AlphaGo played and you calculate how long a human takes to play a game, a person playing as many games as AlphaGo learned during its training would have to have played Go for about 6,830 some odd years. Not exactly practical. The old saying in the 80s was that connectionist networks can't achieve learning in the lifetime of the organism, and as far as I can see, that's still true. Now, compare that to... Yes.
Ken, sorry to interrupt. This is Diane. You may need to pick up your handset because there is kind of a squeak coming through that may be from your speakerphone.
I have no handset.
Oh, okay.
Well,
then,
okay, so consider here the case of a dog. You can teach dogs to train things. Here's a border collie herding sheep. You give them some affection, and what if you could build AI systems that was robust, trainable, and taskable as mammals are? That'd be a major advance in AI. So, hello. That will advance. There we go. So, in our own group's work, we're building the companion cognitive architecture. We're trying to build software social organisms that can work with people using natural modalities like sketching and natural language, that can learn and adapt over long periods of time and maintain themselves rather than having us doing mind surgery on them all the time. Now, we're not there yet. We're far from it. But the whole point is to create systems that are capable of working with people as apprentices. Now, there's a bunch of scientific hypotheses about how we're going to do this. We think analogy is central, qualitative representations are central, but the idea of a software social organism is actually independent of those assumptions. And that's why I think it's important to formulate this as a kind of path towards human-level AI. Okay, so what we see here is keyboard commands that work. Okay, so why think about organisms? Organisms are autonomous. If you work with a child or a student, you don't have direct access to their internal representations. You don't know exactly what your collaborators are thinking when you talk to them, and that's okay. These natural modalities let us get enough ideas across to where we can work together effectively. And if you look at today's systems, as we were saying before about Watson and AlphaGo, those things require someone knowing their internals. You'd like adaptation. You want incremental learning. People learn constantly in everyday life, and we build up that knowledge over long periods of time. And again, this is something that's not really possible with today's machine learning systems. Now, there's a new interest in something called interactive task learning that if you haven't been following that, you might want to start because there's more people working on it now. And the idea is exactly, there's some tasks you have, you teach a system using nothing but natural modalities to interact with it. On the left hand here, you'll see the Rosie robot done by Kirk and Laird in Michigan, and it can be trained to play a bunch of games using natural language and vision. And it carries out the game moves by moving blocks around on a table. On the right here, you see a companion learning to play tic-tac-toe, where Tom Hendricks is instructing it by a combination of natural language and sketching. So, why social? Being social turns out to be a huge driver of intelligence. So if you look at Mike Tomasello's research on how intelligence evolved, his argument is understanding how to interact with other critters like us, conspecifics in their terms, is a very important thing. And if you think about human beings as opposed to gerbils, gerbils roam around in the world, they find food, and they do all sorts of physical things. But humans have culture. So none of us here have lived through the American Revolutionary War. None of us here have directly seen a molecule except through the eyes of a scanning electron microscope. And so we can think about these things even though we've never physically experienced them. And that's a very human characteristic. Stories are a way we teach each other things. Patrick Winston's work is probably the best known in AI. There's tons of other people in different fields who made this argument and have pushed this line. And the thing about smart organisms is they want to cooperate and collaborate, not just compete. And if you look at Barbara Gross's work, she's done some very nice work starting to explore this. So organisms are good because they're autonomous and they adapt. Social is good because we want things that work with us and collaborate and cooperate. And so human-level AI, I think, is going to just end up being social organisms that are really smart. So a gerbil is a social organism. Building a software gerbil would be interesting, but I don't think it's going to be a direct thing on the path to human-level AI. And what I mean by sufficiently smart is that it's capable of learning to perform a broad range of tasks that people do, performing as well or better than they do. That's an extremely high bar. We're nowhere close to that. But the cool thing about that bar is if you pick your spots carefully, there's lots of incremental progress to be made, and there's lots of incremental value from making that progress. So you can imagine, for instance, in education systems that would be fantastically useful even if they couldn't handle the full range and breadth of human knowledge, but happen to be really good science nerds and really good at explaining things to children. So, what does it mean to build a social organism? You have to teach that apart. And I spent a lot of time looking through the cognitive science literature, and this is my attempt to recast the substrate, the things that any system that's going to be a human-like social organism has to have. It's about necessity. It's not necessarily sufficient, but it's certainly necessary. The first system is autonomy. It's got to have its own needs and drives and capabilities for acting and learning. In some ways, that's basically a recursion to something that's just as hard to define as being a social organism, because autonomy is something that if you look, there's whole conferences about it, there's people talking about the science of autonomy. No one said this is easy. But the idea that your AI system has needs and drives beyond, for instance, here's the task I give you today, do it, which is a current model, right, the tool model. The tool model is showing its age, it's fraying at the edges. They have to operate in environments that support shared focus so you can communicate. So, for instance, here I'm using a pointer, or I could use this clever highlighter to say this is something that's really important. But the interesting thing about this is, functionally, everybody has to have some information about what others can sense. I assume that if you're using a Firefox or a browser that isn't Microsoft Edge, having tried this, that you'll be able to see that highlight. But if you're using Edge, sorry, it doesn't work. I tried it. And participants can make their focus of attention known to each other easily. In face-to-face communications, it's done by things like eye gaze and gesture and facial movements. In telephone conversations, it's done by prosody, those non-spoken language signals that are carried in voice, the emphasis and timing. Do I rise at the end of a sentence, or do I fall at the end of a sentence? Those things carry a lot of information that you can make sense of. You need language, and not just a kind of simple command language, go here now, but you also need to express beliefs. I think John is confused on this point. John thinks that Mary understands where we should go. You need to talk about hypotheticals. If we took that approach, we'd be missing a big opportunity over here. These are all things that humans do with each other and are extremely important for our systems to be able to do with us flexibly. They also need to build models of the intents of others. So that means understanding the kinds of goals they can have, how their actions feed into those goals, and what their needs and drives are as the wellspring of particular goals. So if someone's goal is thwarted, and you understand why they wanted to achieve that goal in the first place, you might then be able to predict how you could help them achieve that goal in some other way. So this kind of reason about each other to be able to objectively explain what it is others are doing, again, relies on that ability to have complex beliefs and hypotheticals. And the final point is something that's very interesting. You want strong interest in interactions with your conspecifics, i.e. things like you. And I'm being generous here in thinking that we're going to be able to make software that can fill that role. If you look at humans, this is a little controversial. Tomasello claims that we're the only primates who really routinely help each other. There's plenty of experiments that show if a little child can show an adult how to do something when they're trying to do some joint task, the child is thrilled and the child is eager to do it. If they think the adult is confused, they will go volunteer to help the adult even if they don't know them. And Mike claims you never see that in chimps. That's controversial. Some people claim that there is some helping, but certainly humans have been called a pedagogic animal. And I think that's actually a pretty good description of us. We're into this kind of activity. One of the nicer things about us, actually. So, implications for evaluation. We're thinking about how to measure AI. Obviously, no single test is going to work because it doesn't measure breadth and it doesn't measure adaptability. It can always be hacked. Question answering, well, I can Google it, or I can go through a lot of work to then make the questions not Googleable. Oh, but then someone posts them somewhere, and then I can cheat that way. That's not really a good way to look at things. So, what you really want to do is evaluate these systems by their ability to participate in our culture. And to me, that means doing real work, interact with people appropriately, and learn and adapt its work, adapt itself about its work and about other people and itself, without us AI experts constantly fiddling with its internals. We don't get to fiddle with the internals of our collaborators, and they don't get to fiddle with us, and that's fine. So this gives us a whole bunch of dimensions to scale the evaluation process. So if you think about the interaction modalities, right now, speech works fine if you're saying something that thousands or tens of thousands of other people have said. Doesn't work so fine for novel things. Vision, there's a lot of low-level object recognition, but it's still nowhere near as stable as mammal vision is if you look at the results in adversarial training. Language understanding is something that's advancing rapidly, but it's still got a long way to go. Mobility is an interesting case. You'd like to build robots that roam around in the world, but one of the things about the whole cultural point is there's a lot of work that isn't physical. There's a lot of room in our society for purely soft bots that are cultural artifacts. And if you look at the massive interest in industrial investment in chatbots, you can see where this is a good thing. I think today's investment is a little dangerous, by the way, because there's a set of expectations being raised that the technology, in most cases, is not going to be able to cover. It'll get better, but will it get better fast enough compared to the very high expectations that have been generated is no question. Some people think you should start with nothing. This is the standard machine learning idea. We should make everything learned by the machine. Well, it's not clear how much prior knowledge humans have. Chomsky used to argue that, still does argue actually, that language must be innate because there's no learning mechanisms powerful enough to learn it. And that just appears to be not true. He also claimed that there's no negative evidence. Anyone who's helped with children for more than 10 minutes understands this isn't true. And now there's been a lot of proposals that you can learn language, for instance, using statistical learning, using analogy, and both of those things are showing great promise in modeling human language learning. Now, you might say, for an AI system, why start with nothing? And I think that's actually the smarter move. There's no reason not to start with a lot of knowledge and make something that's as smart as we are, and then you might go back and solve for how simple can you make it. But why give yourself that big a handicap starting out? Another dimension is the range of knowledge. AI2, the Allen Institute for Artificial Intelligence, kind of went back from working on advanced placement tests because those are very narrow professional tests, and instead went back to elementary school science tests in order to try to look at common sense and how to build things that can learn common sense knowledge. But on the other hand, you'd like something, well, you could, in some sense, what we have is it's easier to formulate, for example, all of the knowledge that you need to understand engineering thermodynamics to do routine design tasks than it is to do elementary school science. I know because we've done the latter, and we've done the thermodynamics, we haven't done elementary school science. The range of tasks something is responsible for. You might have something that's only good at one particular kind of task, and that could be great for applications. You might have something that actually is juggling learning and performing in multiple domains at once, which is much more like what humans do. And of course, it's learning ability. Can learn about its job, its people, and itself, and how effectively. How much data do you need to do it? Andrew Ng has been quoted as saying, even the most diligent parent isn't going to show their child 50,000 coffee cups. And if you're working in an office and you have to show something, how to fill out a form 10 times, 100 times, 1,000,000 times, you're not going to find that system useful. So one thing about humans is we often learn extremely rapidly. And that's something that we need to crack in our AI systems. And finally, let me just wrap up. So to summarize, I think human-level AI is the same thing as a sufficiently smart software social organism. They could be really tied into our culture and look at the world exactly the same way. Human-level doesn't necessarily mean human-like. This is not about imitation. It's about creating things that can participate in our culture in valuable ways and have the same properties that other participants in our culture have. It's not trying to fake looking like them, it's trying to be like them. And the apprenticeship trajectory provides a framework for many kinds of evaluation. So initially, you're a student learning from instructions from instructors to carefully designed exercises. You work as an assistant to a mentor with increasing responsibility. And finally, you work autonomously, reporting back periodically for debriefing and review. Eventually, you take on your own apprentices, and the cycle continues. So that's what I wanted to say. Thank you.
Hey, Ken, thank you so much. Diane, is it okay if I jump in with the first question, or did you want to tell people to get off mute?
Oh, please do. Please do.
Okay, I see you typed in, audience, please press *1 to unmute for your questions. So, Ken, thanks so much. This is, I think this is an excellent research direction for the community. I think the concept of participation in our culture as a test for software social organisms is just a brilliant direction. And to think about the dog level as a great intermediate step, and then the young child level. I'm wondering, where do you think we are as a community on getting behind this direction, and what can IBM do to help you with this? And what sort of where are we on data sets? Where are we on machine learning algorithms? Are there data collection methodologies? How can we help move this direction forward best?
I think there's a couple of things. One of them is to the extent that so for instance, if you're trying to use natural language to interact with something right now, your choices are pretty limited. My group has done a deep dive over the last 17 years, to build up capability in natural language understanding, because nothing off the shelf would work. Just having, like, Google made a big thing out of releasing its parser. That's nice, but it's a dependency parser. It's not it doesn't give you a very detailed answer, and it's only a partial syntactic analysis. So, for instance, I'd love to see the English slot grammar parser be available, maybe through Bluemix, to the research community. You can see the one used in Watson. It's a lovely parser, very cool stuff. So things like that, where funding research on integrated systems, if you look at the kind of resources you need to do this research, it's very expensive. And you have these evaluations that are going to be insanely expensive because you're training something over long periods.
Right. Great. Well, thank you. Those are good pointers and suggestions. Others with questions or comments for Ken? Well, maybe some people are still getting star one and off mute. Ken, could you say a little bit more about the speech acts? I'm currently reading John Searle's stuff on the construction of social reality. And do you have a sense of what level of speech acts these systems need to get to?
Oh, I think we need multiple levels. So in our own work, we've looked at, for instance, the learning tic-tac-toe. There are some communication acts that are about just the basic low level. Are they informing me? Are they asking a question? But then there's a level above that that says they're teaching me something. So what role is this playing in the larger flow of instruction? So there's higher level patterns. You start with those levels. They talk about like inform and question and elaborate. And you go up higher and higher. We've been formalizing this as narrative function because it's a kind of general concept. But like, are they talking about a continuous process? Are they talking about a quantity? So coming up with ways of recognizing these higher level patterns and formulating those, I think is a really important knowledge level contribution to making these systems. And I think these have the same generality as the lower level acts because a lot of human knowledge has commonalities and we can exploit that.
Interesting. Yeah.
So,
go ahead.
Sorry. No, please go ahead if you were finishing the question.
No. Go ahead.
Okay.
I have my time.
This is Bhavna from IBM Research. So, Ken, this is a very good talk, and it just reminds me that my social scientist friends, they've always said that, oh, yeah, we come in where you guys, after you guys have reached your limits of understanding, that's where we come in. And so it just says that we are going towards, we want these computers to really be social organisms. So this is quite interesting. My question to you, while I understand we are still working on very primitive tasks of, we don't understand the language, we don't understand the speech and so on, but have you given any thoughts of where we might be able to learn from the social sciences so far, or is there some learning we can do from them that would help us?
Oh, so a lot of my work and so there's work in cognitive modeling that's been doing a lot of looking at cognitive psychology and social psychology. So, for instance, all the work on emotions in AI that I know of is very much informed by social psychology. So it's being exploited already. So they even use they've taken the theoretical. So, for instance, emotions. There's beautiful work on that in social psychology, but it's not very computational. So an appraisal theory doesn't say how the appraisals get done. So what AI people have been doing is figuring out some computational stories for that. Like the knowledge that you have to talk about events in the world and your goals and intentions. They say, hey, we can formalize all that by using the kinds of representations down in AI planning systems. And then we can say, well, maybe appraisal is done by rules in parallel. Or maybe appraisal is done by a combination of rules, but also analogy. So one of my students actually built a model like that, where that kind of rapid feeling you get says, oh, geez, this might be a bad idea. So we're thinking of that as happening through analogical retrieval. So I think there is a very an existing connection that we're learning a lot from them. It hasn't gone so far the other way, though, in part because these models are so crude that it's hard to make contact. I guess the place where that's happening the most, if you look at the work of the Institute for Creative Technologies at USC, their work on virtual humans, one of the things that they're doing is using that to gather data about people. And so if you think of it, people in social science experiments, the Confederates, who have to do the same thing over and over again to interact with someone, even though, they're stressed or it's hard to do the same thing the 57th time. A virtual human can do that no problem. Its problem is in the other direction. And with modern sensing technologies like Connect and RealSense, the idea that computers can be reading our facial expressions to a degree that even other humans can't is well within the realm of possibility. So these are going to be great new research tools for social scientists as well.
I see. Well, thank you.
Well, thank you, Ken. We're a little out of time. There are a couple of questions in the chat, which I've captured, and I will email them to you. I would like to encourage anybody else to continue the conversation and ask questions on our LinkedIn discussion group. I'll make sure you have all that information, Ken, and thank you so much for being our presenter today. Your talk was excellent.
Thank you. My pleasure, and thank you for everyone for coming.
Thank you. Bye.
Goodbye, everyone. Oh, by the way, there won't be a call next week. I'll send you a note about that. We'll pick up on the 14th. Thank you, everyone.
Bye-bye.